arbitrary loading. Actually, most of the cases you have to do numerical integration rather than the convolution integration, because convolution integration is very limited to some special loadings where the loading can be expressed as some closed form of time functions there. And last time we talked about one of the most popular method called the central difference method. Central difference method is very widely used in a lot of structural softwares, especially some structural software developed to simulate the structures under impact loading, blast loading, where the duration of the loading is very small. Typically, we use the central difference method, and in that case, we can get very stable results. But if you want to have your central difference method work stable for you, you want to make sure that the time step is small enough. It's smaller than the natural frequency of the system over pi, and it's showing on the one node on the node over here, right? In the cloud mark over there. So last time I also assigned a homework for you to practice, and some of you asked me questions about how to program this method using Excel or MATLAB. I haven't yet taken a look at some of your submissions. Looks like the majority of the class used Excel spreadsheet, correct? And I think yes, that's spreadsheet is very powerful. Let's say in this case, and in most cases, you should be able to complete the assignment using the Excel spreadsheet to do the numerical integration. And the last time we started the example, and if we have a half sine with the impulse loading, we should be able to use the central difference method to do the calculation and give us the velocity, give us the displacement, velocity, as well as the acceleration of the system there. So, you should be, and I also shared a spreadsheet that I used to complete this example. I'm not sure how many of you finished your homework based on this spreadsheet, or you developed your own spreadsheet. But you should be able to use this shared file to complete your homework assignment. So, personally, any questions regarding the homework problems? Everybody's in good shape? Yes.
What should we do when data is different? Like, is it 10%, 1%?
Theta is different, and that means if you would like to consider different damping ratios, right, you need to change the C value. As you can see here, anytime when you do calculation, you need to use different damping say coefficient over here. So, for example, if your damping ratio is equal to 0.1, you should be able to calculate the C equal to, because the damping ratio is equal to C over 2 times M times omega N, right? So this C should be equal to 2 times theta times M and omega N. Yeah. Given the theta, you should be able to calculate the corresponding C value. Does that make sense?
Yes, but when C is given, no need for using C, right?
Correct. But either damping ratio is given to you or C is given to you. Yeah. Very good. Very good question. Any other questions? So, if no any questions, we will talk about another the second method. So as you can see here, the central difference method is conditionally stable. In some cases, when the natural frequency is very small, you may have used very small time step. So that means that integration will be very slow, very slow. So in that case, we may have to switch to another method called and I also attached the central difference method procedure, the load shared to you. So anytime, actually this is accepted from your textbook. If you have the textbook, you should be able to use the procedure to finish the homework problems too. So some of you use the procedure on the textbook. So that's why I require everyone of you to get a textbook copy of text, either a hard copy or an online copy, because the textbook has a lot of useful information that we need to complete the assignments as well as projects. So in Elizabeth, have you used this procedure or?
I think I didn't know we had that page.
Mhm.
So I think I had a tutorial where he gave us a lot of those formulas and I was using those.
Mhm.
They look the same, like K hat,
Yeah,
E hat.
they're the same.
Yeah,
Like,
the-
they're the same.
Okay, very good, very good. So yeah, since this is the 500 course, some independent research is expected. You guys did a very good job. If you watch videos or find them online resources, very good job. So this is a central difference method, and tonight, firstly, we will discuss another type of method called a numeric integration. So that is the second method. And after that, we will talk about how to use a numerical method to calculate the response of the structure on the earthquakes. And based on the results of structure response on the earthquakes, we will talk about the construction, especially the definition of response spectral. Because yeah, for some of you working in the industry, I believe all of you have already heard about the response spectral. Anytime when you use when you do seismic design, you have to use the response spectral. So we will talk about what is response spectral and how we can get response spectral, and and also that is very important for you to complete your project. So in your project, you are supposed to, you are required to produce the response spectral for any given earthquake record. So that's the objectives for tonight. So first, let's talk about another type of method, about the U-marks method. Let me. See, it's interesting. So we talk about the second method. Actually, in your textbook, there are more than two methods, but our lecture, we will focus on central difference method and the numeric method because those two are the most popular, and you will see the use of them in a lot of structural software such as SAP 2000, ANSYS, Abacus, StatPro, RESAP. A lot of the structure use this with those two methods. So let's talk about method two, numeric method. So what is numeric method? So numeric method is a family of integration.
Family.
So this is a family of the integration methods focused on acceleration and focused on acceleration. So this is a type of methods that focus on the based on the acceleration. So we will have three types. So type one, constant acceleration. Type two, average acceleration, and type three, linear acceleration. So what does that mean? What does that mean? As you can see, so the response of acceleration of any structure is a function of time anyway. So it's a function of time, so that we should be able to, for example, we focus on the time frame from Ti to Ti plus one. So if we select, so the numerical integration is typically you need to select a time step. So we have the time step here, delta t. So as you have already done in your homework problem, is typically the integration involves if we know the value of the response at time Ti, we need to figure out a way to calculate the response at the next time when the Ti plus one and T plus one. So the numeric method involves the estimation, as you can see here, from between Ti and Ti1, the acceleration and the theoretical acceleration is very, so that we need to approximate the acceleration between and within this time step. Within this time step. So, for example, we assume the at time t the acceleration is ut, and so that and this is delta. So that we can have the at time t, we assume the acceleration is equal to So at a arbitrary time t, and the acceleration can be expressed as a linear interpolation of the acceleration at time I and time I and ti plus one, so that we can have the arbitrary time t, and time can be expressed as the interpolation of time at time I and time I plus one. So this is an approximate. So the theoretic acceleration is, as you can see here, is represented by the blue line, and the acceleration expressed by this equation is approximate, because the approximated acceleration at time t is represented by the dashed red line. But there is a small error there. There is error there. So based on this, we should be able to calculate, if we know that we acceleration here, we should be able to calculate the velocity. So that means the velocity and t can be calculated, because we know that the velocity is the integration of the acceleration. So the acceleration at time velocity at time u should be equal to so the velocity at time t should be equal to the velocity at time I plus the integration from time I to time t in terms of the acceleration. So that's a very simple relationship between velocity and acceleration. Do you agree with me? We have that. So, nothing fancy math here, but just basic calculus. So that we should be able to now we plug the top equation to the bottom equation. We should be able to get the velocity that's equal to in this case, we can express the velocity at time t in terms of the velocity and I and the acceleration of time I and I plus one. As you can see here, numerical method starts from the acceleration. It is different from the central difference method. Central difference method starts from the displacement. We go from different initial conditions here. So similarly, we should be able to get the displacement at time t. So the displacement time t we can do the integration on velocity. In this case, we have already expressed the displacement at time t in terms of displacement, velocity of the acceleration at time t and time I and time I plus one. And time I plus one. Does this make sense? So numerical method starts from the acceleration, and based on the acceleration, we can derive the velocity and the displacement at any arbitrary time within a time step that we have already selected at the start of any program. So based, any questions up to here?
Yeah, I have quick question.
Yes.
What is gamma?
Gamma, oh, delta, you mean?
I mean delta.
So delta is a coefficient for us to do the linear interpolation. And as you can see here, in the first equation there, and so the delta is used to do the linear integration for the acceleration at any time t over there, because we need to if we know the acceleration at time I and the acceleration at time I plus one, we need to approximate the acceleration at any given time t. Right? So the delta is a selected number. For example, you can select the delta equal to 0.5 or 0.3 or 0.7. So it's a selected number beforehand, before you run your program here, so that we can approximate the acceleration at any given arbitrary time in terms of the acceleration at the selected time I and time I plus one. Does that make sense?
Yes, thank you.
As you can see here in the chart on the left side, the actual acceleration is represented by the blue curve, while our approximate acceleration is represented by the red dashed line. So since it's a numerical method, we have to use some approximate value to calculate the actual to approach the actual acceleration over here. So a very good question, very good question. So this is I would say this is just some mathematical tricks developed by Professor Newmark from University of California, Berkeley. Yes.
So do you have to know the plot of the acceleration response to use this method?
No. You mean do we have to have the entire acceleration response? No, we do not have to have that, because for any given external load, the acceleration response is unknown to us. Right? We don't know what the plot of acceleration would be like. Yes.
Professor Newmark's middle name was Mortimer.
That's
Mortimer.
Uh-huh.
Nathan Mortimer Newmark.
That's my one.
And he has the same birthday as my mother
Oh,
and is from New Jersey.
yeah. Smart persons always share the birthdays. So delta here, the delta is a pre-selected number mentioned earlier, but typically we use an beta if we net beta equal to half of the delta, and we can have the displacement So if we let beta equal to half of delta, we can have a formula that comes with in term comes in the expression terms of time difference between time t and the time I over here. So sometimes numeric method is also called numeric beta method. Numeric beta method. Because we introduced a pre-selected number of beta. So there are three popular numeric methods. In the future, if you use some structured software to do time history analysis, the software will ask you to use which numeric method. Sometimes you are responsible of inputting the value for beta. So there are three popular methods. So we have beta and delta. So the first one is called the constant acceleration. And then we have the average acceleration and the linear acceleration. So constant acceleration is between time I and time I plus 1, we have the beta value equal to 0, delta value equal to 0. So that means we assume the acceleration between time I and time I plus 1 is constant. There is no difference in the accelerations within the time step that you have already collected. Within the time delta t, the acceleration is a constant number. It's a constant number. So that corresponds to we have the, so this is the actual acceleration, and we have the I and ti plus 1. So if you use the constant acceleration, that means oops. So this is the method one. So we assume the acceleration is constant. It's constant. And equal to the acceleration at the start of the time step. So that's just as you can see, that's just an approximate because the theoretic acceleration is very good, but in order to make computer to work, we have to assume the acceleration here. And the second one is called average. So we have the beta equal to 1/4, and the delta equal to 1/2. So that means is beta equal to 0. And then we have the beta. This is the beta equal to 1/4. We have beta equal to 1/4. That means we assume the acceleration is the average between the acceleration at I plus 1. And then we also have the linear acceleration. That's we have the beta equal to what, 6? And that means in this case, we'll do the acceleration. And he is linear, he's linear. So the actual acceleration is maybe a curve value, but if we select the beta equal to 1, 6, the approximate acceleration is linear between time I and the time I plus 1. So when you do numerical integration, yeah, we have to do some approximation here. So any questions up here? Does that make sense? So but how can we use the numerics method to find the acceleration, velocity, and the displacement at any given time? If we know the initial condition. Let's talk about the typical procedure here. So, for example, if we take the average numeric method, for example, we have the beta equal to 1/4 and the delta equal to 1/2. And so that the acceleration can be expressed at any time, can be expressed as so that is average means. So the acceleration at any given time between within the time step can be expressed as the average of the acceleration at the beginning of the time step and the end of the time step. So that is average means. Does this make sense? Because beta is already equal to 1/4.
Correct.
We substitute. So yes, we use either beta or delta over here. Because beta is equal to half of delta. Since delta is equal to 1/2, we just express the we just plug in the numbers. Does that make sense? Okay. So this is a velocity. And here, as long as we have the velocity, we can express the acceleration. We can express the velocity in terms of the constant number. That's equal to 1/2. E minus T. Velocity, and we can also express the displacement. So if we please select a value for beta or delta, we can express.
Excuse me.
Yes.
And the second equation for the velocity, should we add the initial velocity to this equation?
You mean initial velocity? So far, no, because we are here. We assume if the initial if the acceleration at the beginning and the end of a time step are known to us, we should be able to express the velocity in terms of the acceleration. The velocity at any given time within the time step in terms of the acceleration at the end and at the beginning of the time step here. So we haven't yet talk about the initial condition yet. Okay, so if you wanted to know how the initial condition influences the results here, we can just assume that I equal to 0. If I equal to 0, we will talk about that later, how we can incorporate the initial conditions, how the calculation can be started. So does that answer your question?
Okay.
Kind of, kind of. Yeah, we will talk about that later. So as long as we have the three equations here, we can get the typically here, as long as we pre-select the time step t, we usually are not concerned about the response at time t. We are more concerned about the response at the time ti plus 1. If time ti is the response at time ti is known to us, we would like to know what is the relationship between the response at a later time with the response at the earlier time, so that we can have the program to calculate the values step by step over here. So how about we just let the time t equal to the ti plus 1. Yeah, that's right. So that we can have the delta t equal to yeah. Right. So we can express the displacement equal to so if we let the t is equal to ti plus 1, we should be able to find out the relationship in terms of the between the displacement at the time or the acceleration at time ti plus 1 and the time ti here. And so that we can solve for the acceleration here. Because typically at the start of a program, the UI is known to us. This is known, and because that's the response at the earlier time, and the acceleration is also known to us at a later time over here, because we approximate the acceleration based on the beta value. So the question here is we can express, we can also express the time, the acceleration in terms of the displacement. So if we move the acceleration at time I+1 to the left side, we can have that equal to so this, and we will use this equation in the program. You have a program. This is one of the most important equations that we will use. So this equation expresses the acceleration at time I+1 in terms of the displacement at the later time and the response at the earlier time. So similarly, we can express the velocity. So the velocity that's equal to so that we can express the velocity at time I+1 in terms of we can also have the acceleration at time I. Sorry, here we should use the, let me double check, something wrong with my note here. Wrong with my, we should, so we have the, okay, let me go back. So we use the back to the initiation here, we have the velocity. Since the acceleration is average, it should be correct. And now we express the okay. So now we just substitute the acceleration because we have already expressed the acceleration at the time t. Actually, we just substitute the top equation to the bottom one. So we will have the velocity here. This should be equal to the velocity I plus we have all this times delta t, right, times delta t, so that we can solve for acceleration at the time t. That's what. So that's equal to minus ui. This is another equation we will use. So we substitute this one. Replace that so that we can express the velocity in terms of the displacement, right? So any questions up to here? Any questions up to here? So does this make sense? So please keep in mind that the numerical method starts from acceleration. And typically, if we know the acceleration at the earlier time, we can approximate the acceleration at the later time, and so that we have the accelerations at the earlier time and later time, both of them known to us. And based on that acceleration, we can express the velocity in terms of the acceleration, here. So now we use the equation of motion. So equation of motion at E is 1. So that we have n so at the time I plus 1, we have the inertial force plus the damping force plus the spring force equal to the external force, right? So at any time, the equation of motion should be met. So now we substitute everything in this equation. So we have already expressed the So we will have the, because we have the acceleration already expressed in that. So we have the 4 times third dot t squared. You will see the equation of motion and equation of motion in terms of the response at I and times I plus 1. So what's the goal for us to derive all these equations in class? Will you use this equation in future? And probably not. The reason why is the derivation of those equations to show how computer works as a black box, in a black box. So now, as you can see here, we have already expressed the equation over here. Remember, we would like for our type of problem, the response at the earlier time is known. Right? If that the response, everything in terms of I are known to us. So the only unknown one is the response at I plus 1. Right? So as you can see here, how many unknowns in this equation? So the everything in terms of I is known to us. So how about the force Pi plus 1? Is that known to us? So the force is known to us because that's the external loading. We should know the force as a function of I1. So what is the only unknown variable in this equation? So the displacement I plus 1, right? So this is the only unknown. Only unknown. So we rearrange this equation. If we know the response at the time I, we should be able to know the displacement at the time I plus 1. So does this make sense? So we solve this equation for ui plus 1, ui plus 1. So we solve for what we can get as ui plus 1 expressed as this is equation. This is the equation. So that means given the response at time I, we should be able to calculate the displacement at time I plus one. Based on this, so much more complex than the central difference method. And this is the initiation of the problem, actually program. So we call this equation one. So this is the equation one in your program. It's equation one. We just go ahead and use this equation to calculate the response. Here. So as long as we have the procedure here is firstly we use equation one to calculate displacement at I plus one. For example, when we talk about initial condition, we can have the I equal to 0. And if I equal to 0, UI, that's the initial displacement. UI dot, that is the initial velocity, and the UI double dot, that is the initial acceleration, right? So if we know those numbers, we should be able to calculate the displacement at time one. So that we can get that number for the displacement time one. If we have a number for displacement time one, we should be use the earlier equations. Yeah. So this is called equation 2. So now this number is known to us, so that the velocity can be calculated using displacement. And then the acceleration, the equation 3. Use equation 3 to calculate the acceleration for time I plus 1. Since all the variables on the right side are unknown to us. So this is the procedure here. So 2, so we use equation 2 to calculate the velocity, and equation 3 calculate acceleration. So step by step, we should be able to get all the responses here. So interestingly here is is
Yeah, is that n? Then n negative EI plus 1. Red line's going right through it.
The n over, yes, that's n over the delta t squared.
Thank you.
Interestingly here is the numerical method that is developed starting from the approximation of acceleration, right? But the procedure starts from the calculation of the displacement and down to the acceleration, right? So as long as we have the initial condition, we should be able to use this method to calculate the response at any given time. And this one is looks like a little bit more complex than central difference method, but there is a benefit. So this method is conditionally stable, unconditionally stable. And this is unconditionally stable. So that means you can have a very large time step. your program can still give you some numbers, But the accuracy may be compromised, but the procedure is stable. That's one benefit from the numeric method. Very smart method. So that's the theoretical background for numeric method, and after the break, we will after a short break, we will talk about how to incorporate this method into your Excel spreadsheet. Okay, so any questions before we have the break? If not, let's resume the class about 10 minutes later, and then let me know if you have any questions.
Do you see cooler and hammer?
Okay, and number one, numerical method.
Oh, shit, we're into this.
So, if we use the similar, the same problem that we seen. So if we use the same example that we used for central difference method, we have a sine wave here. So this is the input. This is half sine wave, so we should be able to get all the data for the P, for the PI or PI plus one. And if we have a system with the given natural frequency, damping ratio here, so that how can we use the numerics method to calculate the response here? So, your spreadsheet. So, online students, can you see the spreadsheet on your screen now? Online students, you?
Yeah, I can see it.
Okay, thank you, Dean. So here, as we mentioned that earlier, so in order to initiate your calculation, you need to know the mass, strain, constant, as well as the damping coefficient here. So those numbers are based on the damping ratio and the mass. So, for example, so the mass is given to us. So based on the natural frequency, we should be able. And the K is also given to us. So we should be able to calculate the C value based on the damping ratio. So we use the same mass, K, and damping ratio here to start the. So now on the left side, if we use the average numerics method, so since we have already derived the formulas to calculate different responses here. So if we use the data t equal to 0.1 second. So at time 1 and time 0, we can have the data for the force. Since it's a sine wave, half sine wave, so we have some values between 0 and 0.6 seconds, and anything else is the 0. This makes sense. So now, initial condition at time 0, we have the initial condition, the initial displacement, acceleration, velocity, and the acceleration should be all of them equal to 0. So the next step, we can just go ahead and implement the the equation to calculate since the displacement at time I plus 1 at time point 1 only a function of the initial condition as well as the PI here, as you can see here. That's only a function of those and the delta t here. So that we should be able to do the calculation here. So we can find that the UI firstly, and then we can get the velocity. And velocity is the function of the displacement at time I plus 1 as well as time I. So that we can have the velocity and then the acceleration, and can also express the acceleration in terms of the displacement at the earlier time as well as the current time. So that we got all the numbers. So we do the same procedure. And we can just do it as a copy all the equations here, right? So that we calculate all the numbers here. So this, I would say that numerics method is more straightforward than the tensor difference method, as we have say here. So now let's compare the result here. So I have already you can see here I compared the theoretical result. So the theoretical result is in red. Central difference method is in blue, and the numerics average method is in black. So there are some errors between the average, between the numerical methods and the theoretical method there. We can control them. We can control them. For example, if we change we can use a finer time step here. We use half of the time step here. So if we use a finer time step here, what happens if you take a look at the central difference method here? So if we use 0.05 second time step here, so have we got the more accurate result? We get the more accurate result. So typically, for both methods, the central difference method or the numerical method, if you use the finer time step here, you will get the more accurate result. But if you use the finer time step here or smaller time step here, typically will produce more data, and calculation will be slower to compromise that. There will be some compromise of the computational efforts or time here. So this spreadsheet has already been shared on Blackboard, so you are welcome to download it and play it a little bit. So for example, we can try 0.2. Those are 0. So this is the point two. We enlarge the time step. The arrows is bigger, much bigger. So that's the numerical method. So as long as you follow the procedures for both methods, you should be able to get get it work. And I think this is the start of your project. You may also use the spreadsheet to help you finish your project over here. So any questions regarding this example over here? And since this procedure is very standardized, I'm not gonna show you how to use Excel. I believe you are already expert in using Excel spreadsheet, so I'm not gonna spending time to train and to teach you how to use the spreadsheet. So that's the numerical method. So with the powerful numerical method, basically, we should be able to do the calculation for earthquake. So for earthquake, we just need to input the external force, the earthquake force here. Here we have an upside wave. If we have an earthquake here, we do not change anything here. We do not change any equation here. We only need to change the input. Right? Earthquake load, plastic load, impact load. Only thing we need to do is to copy the loading data here to get the response here. Displacement will not get explanation here. And that's the standardized procedure we can use to calculate the response of a structure under any given load. So now we are ready to, with the help of numerical methods, we are ready to figure out the response of structure and earthquakes. So now, let's talk about the method response for structure on earthquakes. So that's one of the most important topic in this course. And in future, if you work in the structural design or construction industry, you will see a lot of cases. Response of structures under earthquakes. So here are the objectives of this topic. Actually, this is in chapter 8, your textbook. Chapter 6.
Scary.
We have already covered a lot of chapters so far. One. Response spectrum. Any given and run motion record, you are expected to be able to calculate the response spectrum. To be able to tell the difference between response spectrum and design spectrum. The seismic design or earthquake, the design, you will use the design spectrum. What is design spectrum and what is the difference between response spectrum and the design spectrum? And how design spectrum is developed? That's what we talk about tonight and as well as next week. So firstly, it's so we talked about the response of the spectrum earthquake at the very beginning of this semester. So now I have a very short review on what we talked about. I think about the calculation of earthquake response. So we have let's consider a frame structure. So that can be more than the single degree of freedom. We have a frame here. And then the floor is rigid. So when we talk about response, we would like to know assume the displacement of the response is equal to mu under earthquakes. So we have some ground acceleration. So earthquake, the earthquake record is typically recorded as acceleration because it is the easiest way to record an earthquake. So what is the equation of motion? Equation of motion, actually we talked about that. So the the equation of motion here can be expressed as inertial force times the damping force plus the spring force equal to the external force. Right? So the basically aware of that the UR here is the relative displacement between the floor and the ground. And so that we can express the vibration of the structure as a forced vibration, forced vibration. And the force can be expressed as the mass of the system times the ground acceleration times -1. So the mass here. C. So the system can be is equivalent to the system so initially so the structure is fixed to the ground and the ground has some acceleration and the structure is vibrating there. So the system here can be equivalent to a system where the ground is fixed. There is no motion in the ground, but the floor will have some relative displacement, and where we have a equivalent force here. So that's very important. That's very important. So that means in future when you do that analysis for a structure on earthquakes, you do not have to force the ground to move. You only need to fix the ground and then put a force on top of the mass, on top of the mass. So this two systems equivalent. The only thing here is the calculated displacement, velocity, as well as the acceleration. They are relative values. They are relative values, and we are only interested in relative values here. Why? Because we need to design the force. We know the force in the column is only a function of the relative displacement. Right? So the deformation of the column is only a function of the relative displacement. It has nothing to do with absolute displacement there. So any questions up to here? We covered this at the beginning of this sentence. So we if we divide the mass on both sides, if we divide the mass on both sides, we will have a different And so the problem can be simplified. So the response here, so the mass, spring force, sprinkle constant as well as the damping coefficient can be condensed into the natural frequency as well as the damping region. And then typically, to solve this problem, we can use either the convolution, an integral, or the numerical integration, depending on the type of the acceleration, depending on the type of acceleration. So any questions up to here? Here. So another important concept here for earthquake load is the seismic load, the equivalent seismic load. Or a lateral force. So this is very important because we wanted to do design. If you remember, when you do steel or concrete design, we need to do structural analysis. Right? We need to know how, what is the magnitude of this external force. If you have a beam, we would like to know the magnitude of the distributed load or concentrated load. But for earthquake, what is the load we should apply to the structure? So that is defined as the finding of the equivalent force. And if applied static force to equals this is the structure. So when we do structural analysis, in order to design, for example, we have a structure here, we want to make sure the structure is safe under earthquakes. So that we need to calculate the shear force as well as the moments, bending moment on these two columns. So we need to know what is the external natural force. If this is an external natural force, actually can be expressed as the height h, and so that we can calculate the so under the equivalent natural force, the reaction forces in the foundation, okay, should be able to calculate it. The moment as well as the shear force, okay, calculate based on structural analysis. Right. So what is the equivalent natural force actually? Equivalent natural force here. So should be equal to, that's string constant times the relative displacement, And that's equal to. Similarly, for base here. And the shear force in the base should be equal to this moment. Shear is equal to the lateral force. The moment is equal to the lateral force times the height of the column. So when you do structure analysis, if we can calculate the displacement of the mass, we should be able to tell the reaction force in the foundation, as well as we can show the shear and moment diagrams of the columns. So that is very important for our design. But for design, we just design for the worst. And we design for the worst case scenario because the equivalent lateral force is a function of time, right? Can be equal to 0 and it can be very large in one direction and very large in the other direction. So when we do this, so the moment and shear forces vary with time in the columns. So we would like to know what is the maximum. And that means that we just design for that. Maximum. This corresponds to maximum. Relative displacement. Maximum relative displacement. Does that make sense? Huh? So the structure is vibrating. So when the structure hits the maximum displacement, then the structure will have the maximum shear force and the bending moment here. So the goal here on the rope squeezing is to figure out what is the maximum displacement. So that we can get in order to find out, but when you do the design over here, the question here is
with ITS,
yes,
put a timer on this projector. So I'm just, whenever your class is over at 10 p.m., right?
yes,
Probably like 15 minutes before 10 p.m., I'm gonna put a timer so this projector turns off
okay,
at 10 p.m.
okay, that's good. Thank you. Okay, so as you can see here, when you do design, you want to design for the worst scenario case, and we would like to know what is the maximum displacement for the structure. But the question here is before you design, we don't know this, what the, for example, for the column. And if we have a circular column, so we don't know which diameter, what size of the diameter works for the given earthquake. So for example, if we have a 12-inch diameter column over here, and we know that the maximum displacement is a function of the size of the column, right? Because the size of column determines the K value of the structure. And if the K value changes, the maximum displacement changes. Does that make sense? Because the response of the structure is under earthquakes is a function of the K value. So that means that given an earthquake, firstly, we need to know what size we should start from. So that's why the engineers developed the response spectrum. This one. Now let's talk about the relative displacement. Response spectrum. Expressed as so the response spectrum of we use the S. The displacement response spectrum is a function of damping ratio as well as the natural frequency of your structure. And so that's expressed as the maximum displacement. Maximum absolute displacement. So mathematically, the response spectrum is a function of the damping ratio and the natural frequency for one earthquake, right? And the spectral values is determined as the maximum absolute values of the displacement response. So let's further explain what does that mean. So firstly, we have the input, right? The input. So the input here, that's an earthquake around the motion. For one earthquake record, so we may have for example, this is the recorded earthquake. Earthquake usually starts from a small acceleration and that goes to the peak into two opposite directions, and then fades away. Typical earthquake. So this is the input. With this input, we should be able to feel the force. So now, given a structure, for example, this structure has the natural frequency equal to 0.5 second. Then we have the sampling ratio equal to 2%. So we so if there is a so under this earthquake, the equivalent earthquake, the equivalent force can be expressed as minus m times UT prime. So using the numerical methods, that's the way discussed in this class, we should be able to calculate the displacement for the mass. To be able to plot that. This is the response of the mass here. So that's the URT. So that makes sense. So this is the force Pi. We have the force PT here. And the force here, this force is applied to this structure. If we do the numerical integration, we should be able to tell the displacement of the mass in terms of the function of the time, right? So for example, now we should be able to find the maximum displacement, the absolute maximum displacement. So for example, the maximum displacement here, that's equal to 2 inches. For example. Does that make sense? For any given earthquake, for a selected structure with the natural frequency equal to 0.5 seconds and sampling ratio equal to 2%, we should be able to find out the response of the system as a function of the time, and we should be able to figure out the maximum wind. Makes sense? Right? And now we should be similarly a different structure. The structure has a higher natural frequency with the same damping ratio. We have the same earthquake. We would like to know the response of this. The response may be a little bit different, example, for this structure, the maximum displacement may be 6 inches, maybe 6 inches. Does that make sense? So same earthquake. If the natural frequency of the structure changes, the response changes, and the maximum value may change here. And then we do another different temperature ratio here, in terms of frequency here. When that's equal to 2 seconds. Eight inches. The maximum maybe 8 inches. Maybe 8 inches. Make sense? Huh? So now we would like to do more example. The TM maybe up to 50 seconds. So that the response may be different, maybe different. So then we should be able to draw the response spectrum. So this is the
5 or 50?
50 seconds. So now we draw that maximum displacement as a function of the natural frequency and natural frequency. So for
This only take like 3 seconds. Every 8 hours, this projector will turn off. You're good. You're solid. Can you just make sure to turn off the system before you leave?
okay, turn off the
Yeah.
okay.
The smart.
Okay. Thank you. Thank you. So
Now the thing's just gonna turn off though, at 10 o'clock on the dot.
Yeah.
The whole thing.
We'll be like in the middle of the most important part, like for homework, it's important you know that it's like.
So okay. So for metro frequency 0.5, we have the maximum 2 inches. Then frequency equal to 1, we have 6 inches, and metro frequency is equal to 2 seconds, and the maximum equal to 8. So we should be able to find the three 8 points here, 3 data points here. And if we have a computer, we can have the lecture frequency more densely spaced. So from 0 to 0.5 seconds, we may have more lecture frequency there, so that we have more data points. The same internet over here. So in this case, we may have a something like this. So now this curve is called the response displacement response spectral for the given earthquake, and the structure has a damping ratio equal to 0.02. This is a spectral. This is a displacement response spectral. So this is very important and very useful, I have to say. Why? Because given the structure with a given lecture frequency, I can tell based on this curve, I can tell what is the maximum displacement for that structure without any numerical calculation. So this can be pre-calculated. Right? So now we should be able to design for the spectral. Now we can find the maximum force that's equal to K times the maximum that means for any given earthquake, we should be able to tell the maximum equivalent network force applied to the structure if we know the lecture frequency of this structure and the damping ratio of the structure, so that we can use the spectral to quickly figure out the maximum load effect on that structure. So this is one of the important conception for in structural dynamics as well as for seismic design. So any questions up here? Yes.
This is just like a general question. The damping ratio of like a structure, is that like the stiffness, or is that?
A very good question. The damping ratio is different from stiffness, because we know for stiffness we use K to reflect the stiffness of the structure. Damping is different from stiffness, because damping and for a structure damping is usually the result of friction force between the friction between different structural components, or some damage, I would say acceptable damage during earthquakes, such as the cracks in concrete, yielding of steel, or some micro changes in the materials. So that's why it's different from stiffness, right? Because we know that crack cracking of concrete and the yielding of the steel, they are independent of the modulus of elasticity of the material. Right? So damping is different from them. Okay. But how can we evaluate the damping of the structure? Evaluating the damping of the structure is still a challenging task for engineers nowadays. So the only way to know the damping ratio is to do some dynamic tests. So we cannot calculate the damping ratio based on some theoretical derivatives, such as if you give me the material properties of the structure and the geometry of the structure, and if you ask me to calculate the damping ratio, no, I cannot do that. The only way I can get the damping ratio is to do the dynamic test, either to have the structure to do free vibration or to have an excitation force there to have it to do some forced vibration so that I can get the information of the damping ratio. And also, I believe, I remember at the beginning of this class, this semester, we mentioned that damping ratio is typically, generally, damping ratio is a little bit related to the material you use for the structure. For example, for steel structure, and the damping ratio is around 2%. And if you have a timber structure, the damping ratio may be a little bit higher. Timber structures, we have a lot of gaps between beams and columns, so on earthquakes, those gaps and contributed to the damping of the structure, as well as the friction between different timber structures may contribute to the damping. So in that case, we may use a little bit higher damping ratio for timber structures, maybe 4% or 5%. So that's just general damping ratio that we can use for design. And if you look at the IBC code or AASHTO code or ASC code, typically for building or steel structures, or for building or bridge structures made from steel or concrete, we may be able to use 2% or 3% damping ratio when you do design. And that's close enough to the real case. Does that answer your question? The damping is very complex. If somebody can develop a method to calculate the damping ratio of the structure based on some theoretical numbers, I would say that person will get Nobel Prize for physics, I believe. Damping ratio is very it's very difficult to calculate it theoretically.
It's a research project.
Okay. A very, very good question, because anytime we need to design, we need to assume some damping ratio for structures. But if there is no damping for the structure, the response of the structure will be much more higher than the structure with even very small damping. You will see when you do that project, if you change the damping ratio structure, you will see that how much the difference is. Very good question. So, any other questions up to here? So this is as you can see here, we have the S and the D. Right? The D here represents displacement. So S sub D, that's the displacement response spectrum. Sometimes we also would like to know the velocity response spectrum. Let's talk about another response. So we typically use this called the ULO. velocity. Why we call it zero velocity? Because here it's not the actual velocity response. It's zero because here we need some assumptions here. So we assume the maximum string energy is converted or to kinetic. So that means that the maximum kinetic energy should be equal to the maximum string energy here. So that we have the so we have the half times the mass times the maximum velocity square should be equal to the 1/2 times the string constant times the maximum displacement square. So this is the reason why it's zero because in reality, not all the conversion between the string energy and the kinetic energy is not always equal to each other. It's not always because there are some dampings. Right? So some energy will be dissipated to other types of energy, such as heat or fracture energy to fracture concrete or some damage energy to yield the steel. So this is so based on this, we should be able to tell the relationship between the so that the zero velocity response vector can be expressed as the natural frequency times the displacement vector. So this is the zero is because this assumption. This assumption is not always correct. It's not always correct. It says something in the system is simply is conservative. So actually the actual maximum velocity should be smaller than the velocity expressed as the velocity response vector because there is damping, right? So part of the string energy is converted to the kinetic energy, and then part of the string energy will be dissipated to other types of energy, such as heat or fracture energy to fracture concrete or yield steel. So that means in this case, if we use zero velocity, this one is larger than the actual velocity. So this is so design-wise, this is conservative. We overestimate the velocity in the system if we use the zero velocity response spectrum. Does that make sense? In this case, we have more. And this card then. Zero. And then this spectral value, the zero spectral value is not equal to the actual maximum velocity. And so the zero, we can remove the zero only when the temperature equal to zero. If the damping ratio is not equal to zero, it's zero. The temperature is equal to zero. Actually, our assumption is correct. Our assumption is correct. So does that make sense? And another important and the most important response spectra is called the acceleration, zero acceleration spectrum. Also zero. So if we assume the maximum, a larger force is equal to the maximum spring force. Assume the maximum. So this is the maximum inertial force. So the mass and the maximum acceleration is equal to k times the maximum displacement. So that we can get the similarly, since we have damping here, this A will also conserve B. It's called zero because the zero spectral values is not equal to the actual maximum acceleration. Only when there is no damping, that's correct. But only when there is no damping, we can call we can remove the zero here. We can remove the ruler here. So actually, when you do design, the design spectral is based on the zero acceleration response spectrum. So that next time we will talk about the relationship between design spectrum and the response spectrum, as well as how we can interpret the scientific design specification in a lot of structural code, such as ASTO, IBC, ASC. What's the relationship between those specifications and with the structure dynamics? I think that's all for tonight, and we will continue the topic of the response spectral next week. And thank you for your time, and probably I will give you some kind of
Turn off. But he said like at 10 o'clock.
Okay, thank you. Any questions?
Can I ask a quick question about the last homework? Just very quick question, if you don't mind.
Okay. Sure, go ahead.
Okay, so in problem 5.4, it was required to reduce the time step from 0.1 to 0.05. How can we just find out the corresponding forces?
We're talking about problem 5.4.
5.4. Yep.
He's got a post this?
So repeat the problem.
Wait.
5.3 using data equal to 0.05 seconds. How does the time step affect the accuracy of the solution? So in order to answer that question, you need to compare your results using data equal to 0.05 and 0.1, right? So which one will be more accurate?
I understand. My question is specifically for problem 5.3, it was given the forces
It's called
at 0.1
like
second and at 0.2, 0.3, 0.4, 0.5, and 0.6. Now, when we reduce the time step to go from 0 to 0.05, 0.1, what will be the force at 0.05? So I have to plug this in the table so I can generate the curve. I only have the force at 0.1 as 5 and at 0.2 as 8.66, but I don't have in between.
Okay. Can you share your screen to me, or?
Yes, I can share the screen.
Okay.
One second.
Professor, can I ask a quick question before you guys get into it?
Can you see my screen now?
Yes.
Okay.
So Hisham, so Mikhail has a very short question here.
Okay, sure.
So Mikhail, please go ahead.
Yeah, so I just have some quick edits to make on my homework before I submit it. Is it okay if I submit it tomorrow?
Yeah, it's okay. If it's tomorrow, yeah, that works good.
Okay.
Yeah.
Yeah, I was out of state for the weekend, so I didn't get to work on it too much.
Okay.
But you get it tomorrow. Thank you.
Yes. And if it's past 0.6, it should be 0.
okay, but I got this one. But all of them are negative. Like what zeros and that's it.
Yes, put 0. Because after 0.6, all of them are equal to 0. Just put them on the 0.
Like, thank you.
There we go. So Hisham, yes, I'm with your Excel.
So you see my Excel file here?
Yes.
Okay, so now this is the original table. This is the given information here. At 0.1 second, I have the force as 5. And at 0.2, I have the force as 8.6602. Now in problem 5-4, I will need just to reduce the time step to go from 0 to 0.05. How much will be the force at 0.05, for example, because that was not given in the curve. It was only given at 0.1 as 5. So should I just interpolate between 0 and 5 and just consider it as 2.5?
Correct. Yes, you can. Yes, yeah. You can do the interpolation there. Yeah, yes. If if the force is not given. So what type of force is that? Is that a sine wave or an?
So if you read the problem 5.3, this came from example 5.1, and if you go to example 5.1.
Oh, since it's a sine wave, the function is given to you, correct? That's you can the p should be equal to 10 times sine pi times t over 0.6. So here you the best way for you to do is to input the function for pi other than the numbers for pi.
Where is the function again? I'm sorry.
The function is given in your textbook. That's half sine wave. So that's 10 times, the amplitude is 10 times sine pi times t over 0.6. That's on page 161, right?
161?
Yes.
Okay. I'm trying to find that. Yeah. So the force, okay, I see. So 10 sine pi t over 0.6.
Yes.
Okay. That's clear. Okay.
Yeah.
Okay, perfect. I didn't see that. Thank you.
Okay, so that solves your problem here.
Yes, so this will answer my question. I didn't see the function of the p, so I thought that I will need to interpolate between whatever giving values at certain time step. But since the function is given, so I can just substitute in this function and then I can get at any time, correct?
Yes, correct.
Okay, perfect.
Yeah.
Okay.
So that would be a little bit different from the interpolation values there, but not so much difference regarding the results, you will see.
Okay.
Yeah. Okay,
All
great.
right.
Yeah.
Thank you.
Any other questions for me?
No, I'm good. Thank you.
Okay, great. See you next time.
Thank you. Bye.
Enjoy your week, evening.
You too.